This is Lecture 2, Describing Data. By the end of this lecture, you should be able to identify a variable's unit of analysis, classify a variable's level of measurement, calculate the mode, median, and mean of a variable by hand, calculate summary statistics in Stata, create a bar graph and a histogram by hand, create a bar graph and a histogram in Stata, interpret a bar graph and histogram, calculate and interpret the variance and standard deviation of a variable by hand, and calculate the variance and standard deviation of a variable in Stata. So, as the title of this lecture suggests, we are going to talk about describing data in this lecture. The first step in describing a variable is describing its operational definition. The operational definition of a variable includes its unit of analysis, its classification based on its unit of analysis, the values the variable takes, the meaning of those values, and the source of the data for the variable. In the next set of slides, I will review each of these in detail. First, the unit of analysis just tells us who the subjects are in our study. It tells us who or what they are, where they live, and when they existed. Our subjects could be individuals, or states, or even legislatures or parties. We can focus on subjects in 1 year or many years. For example, if we are going to collect data on parties' candidate selection procedures, we could collect data on political parties in 11 advanced parliamentary democracies from 1972 to 1990. This would be the candidate selection variable's unit of analysis. We have to identify a variable's unit of analysis because if other scholars want to apply our findings to other cases that are not in our data set, they may only be able to apply our findings to cases that are similar to the ones in our data set. For example, if we are only examining parties in advanced parliamentary democracies, it might be difficult to apply our results to parties in younger democracies. Parties in younger democracies might behave differently than parties in older democracies. As such, we have to be forthcoming about the data we use so other scholars are aware of which cases our findings apply to. After we identify our unit of analysis, we can classify our variable based on our unit of analysis. Our variable could be a case study, a cross-sectional variable, a time series variable, or a cross-sectional time series variable. If we only have one subject in our variable in one time period, we would have a case study. If we only have one subject over multiple time periods, we would have a time series variable. If we have multiple subjects in one time period, we would have a cross-sectional variable. And if we have multiple subjects in multiple time periods, then we have a cross-sectional time series variable. So, if we only want to examine the Democratic Party's candidate selection procedures in 2016, we would have a case study because we would only have one subject, the Democratic Party, with one observation in 2016. If we examine the Democratic Party's candidate selection procedures from 1945 to 2016, we would have a time series variable because we would only have one subject, the Democratic Party, in multiple time periods, 1945 to 2016. If we examined all political parties in all countries' candidate selection procedures in 2016, we would have a cross-sectional variable because we would have multiple subjects, all political parties in all countries, with 1 observation each in 2016. And finally, if we examined all political parties in all countries' candidate selection procedures from 1945 to 2016, we would have a cross-sectional time series variable because we would have multiple subjects, all political parties in all countries, with multiple observations from 1945 to 2016. It is important to note that for the most part, you will not be working with case studies in your statistics courses. Since you only have a small number of observations in a case study, you cannot use statistics to analyze that information. The next step in describing a variable's operational definition is identifying how you coded the variable. You have to describe the specific values your variable takes. For example, if we wanted to collect data on party control over candidate selection, we could code the variable like this. A 1 would indicate that a party has no criteria for selecting candidates. This would be the least control a party could have over a candidate selection. A 9 would indicate that the selection is made by an executive party council. This would be the most control a party could have over candidate selection. And the values in between 1 and 9 would indicate variations between these two extremes, with lower values indicating that local party leaders have a lot of control over candidate selection, moderate values indicating that local party leaders and national leaders share control over candidate selection, and higher values indicating that national party leaders have a lot of control over candidate selection. The last step in describing your operational definition is identifying your data sources. There are many places we can find data. We can conduct a survey or experiment. We could use data from government or organization websites. All of these are known as primary sources. Alternatively, we could rely on data that other scholars have already collected. This is known as secondary data. For example, for the candidate selection variable, you could consult political party websites to collect the data. This would be a primary source. Alternatively, you could use reference books on political parties in different countries written by other scholars. This would be a secondary source. After you have described your variable's operational definition, the next step in describing your variable is identifying its level of measurement. The level of measurement tells you a lot about the meaning of the values that your variable takes. Based on what values your variable can take, your variable is either a nominal level variable, ordinal level variable, integral level variable, or ratio level variable. Nominal level variables give us the least amount of information, while ratio level variables give us the most amount of information. An easy way to remember the order in which these classifications give us the least and most information is the French word for black, noir. Nominal, ordinal, interval, ratio. In a nominal level variable, we divide our subjects into different categories. The categories are exhaustive in the sense that we included all possible categories. Categories are also mutually exclusive. If a subject in our variable can fit in one category, they cannot fit in another category. For example, if we wanted to measure someone's marital status, we can place them into 4 potential categories: single, married, divorced, or widowed. This variable includes all potential categories, and a subject cannot be in more than one category. Note that while there is a numerical difference in these categories, 0 versus 1, for example, these categories do not have any inherent order. While 1 might be numerically greater than 0, married people are not inherently greater than single people, and widowed people are not greater than divorced people or married or single people. Since there is no inherent order in this variable, it is a nominal level variable. In an ordinal level variable, we divide our subjects into different categories. The categories are exhaustive in the sense that we included all possible categories. The categories are also mutually exclusive. If a subject in our variable can fit in one category, they cannot fit in another category. Note that there is inherent order in these categories. However, the actual spaces between these categories are not fixed. The candidate selection variable is an ordinal level variable. There are different categories. The categories are exhaustive in the sense that we included all possible categories. The categories are also mutually exclusive. If a party's candidate selection procedures can fit into one category, they cannot fit into another category. Also note that there is inherent order in these categories. The variable goes from least control over candidate selection to maximum control. However, the actual spaces between these categories are not fixed. For example, there may be a small substantive leap between a 2 and a 3, but a large leap between an 8 and a 9. Interval level variables have order, and the spaces between values are fixed, but they do not have a true zero. An example of this could be an ideology variable that arbitrarily ranges from -100 to 100, with -100 indicating very liberal and 100 indicating very conservative. 0 in this variable has no real meaning, since we could simply have made the scale 50 values back and had a scale from -150 to 50. Ratio level variables have order, the spaces between values are fixed, and they have a true zero. An example could be military spending. It could range from a value of $0 to any positive value. Note that ratio level variables give us the most information about our subjects. In this example, we know exactly how much a country is spending on its military. The next step in describing your variable is identifying and interpreting your variable's measure of central tendency. The measures of central tendency tell us the average or typical case in our variable. There are 3 ways to measure central tendency: mode, median, or mean. The mode is the variable's most common value. The median is the observation that takes on the middlemost value when ranking the observation from lowest to highest value. And the mean is just another word for the arithmetic average. So to calculate a mode, you arrange the observations in your variable from the smallest value to the largest value, and then look for the most commonly repeated value. For example, imagine our variable took on the values 1, 1, 2, 3, 4, 5, 5, 5, 7. These values are arranged from smallest to largest. 5 is the most common value, so 5 is the mode. The median is the middlemost value in the variable. First, we arrange the data from the lowest value to the highest value. Then we look at the observation that is the middlemost observation, with 50% of the observations below it and 50% of the observations above it. In order to find the median by hand, we arrange the data from the lowest to highest value. Then we calculate the median observation number. The position of the median for a variable for an odd number of observations is the number of observations plus 1, and that number divided by 2. So going back to our previous example, this is our variable, arranged from smallest to largest. There are 9 observations, so to find the middlemost position, we calculate 9 plus 1 and divided by 2, which is 5. We look for the 5th number, 1, 2, 3, 4, 5, and it is 4. So 4 is the median. In the previous slide, I taught you how to calculate the position of the median observation when you have an odd number of observations. When you have an even number of observations, it is slightly different. First, you arrange the data from the lowest to highest value. Then, to calculate the position of the median observation, first you take the number of observations plus 1 and divide that number by 2. When you do that, you will get a number that has a 0.5 in the decimal. For example, if you had a variable with 10 observations, like this one here, 10 plus 1 divided by 2 is 5.5. But there is no 5.5 observation. So what you do is take the average of the observations below and above this number. So in this variable, you would take the average of observations 5 and 6. Observation 5 took a value of 4, and observation 6 took a value of 5. The average of 4 and 5 is 4.5. 4.5 is the median. In the next slide, I will discuss in more detail how to calculate the average. It's called the mean. The mean of a variable is simply the arithmetic average, or in more specific terms, it is the sum of a set of values divided by the total number of observations. When we denote a mean of a variable in statistics, we use the symbol x bar. Uppercase sigma indicates the sum of a set of values, and n indicates the number of observations. Applying this to an example, imagine we had a variable that took on the values of 1, 1, 2, 3, 4, 5, 5, 5, 7. We have 9 observations. 1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 5 plus 5 plus 7 divided by 9 equals 3.7. 3.7 is our mean. Calculating the mean, median, and mode can be cumbersome. There is an easier way to do it in Stata. To get the mean, you simply type in some variable name into the command box and click enter. In order to illustrate how this works in Stata, I will use the stats review dataset. I want to know the average of the candidate selection variable. I typed in sum can select into the command box and pressed enter. The mean was 4.213779. To get the median, you simply type in UNIVAR in the variable name into the command box and press enter. So in Stata, I type in univar can select, press enter, and the median is 5. Finding the mode in Stata is a bit tricky. You first have to install a program called modes. To install the program, you type in help modes into the command box and press enter. You click yes when the search box pops up, and you have to click on the correct file and install it. In this case, it is here. Okay. Now it is permanently installed in your Stata. Now you can type in modes, the variable name here into the command box and press enter. So I'm going to type in modes, can select, and press enter. And the mode is 2. So now that you know that there are 3 measures of central tendency, when should we use the mode, median, or mean? Which is the best measure of central tendency? The answer is it depends. Here are some general rules to follow. If you have a nominal level variable, you should always use the mode. The median and mean do not make sense with the nominal level variable, as the median and mean assume a variable's values have order, and the nominal level variable has no inherent order. With ordinal, interval, and ratio level variables, if the variable has multiple modes, use the modes. It demonstrates that there is not one single typical case in the data. Instead, there are multiple typical cases in the data. If, on the other hand, the mode, median, and mean are about equal, just use the mean. If the mean is significantly greater than the median, or the mean is significantly less than the median, then use the median. As I will demonstrate in the next part of this lecture, if the mean is significantly greater than or less than the median, then that means there are major outliers in the data. In other words, while most of the observations in the data set have similar values, there are a handful of observations in the data set that take on extreme values. If that is the case, the middlemost value of the data set, or the median, gives us a better idea of what the typical case in the data looks like. Of course, these are general rules on which measure central tendency to use. You should examine your variables closely to determine which measure to use to reflect the typical case in your data set. The last characteristic of your variable that you should describe is how your variable is distributed. Note that this discussion only applies to ordinal, interval, and ratio level variables, as these variables assume order. The distribution of your variable can tell you a lot about what values your variable typically takes on. Imagine you have two different variables with a similar mean, but with different distributions. You have a variable where there are 3 5s, a 0, and a 10, and the average is 5. And you have a variable with 2 zeros and 2 10s, and the average is also 5. But in the first variable, most observations are clustered around the mean of 5. We would say there is little variance in this variable. While in the second variable, most observations are dispersed away from the mean of 5. So we would say there's a lot of variance in this variable. As you can see, these are very different variables, and just knowing the mean is not enough information to tell us what the typical case in the data is. Dispersion also tells us a lot about the values the observations take. One way to illustrate the dispersion of your variable is a bar graph or histogram. For ordinal level data, you use a bar graph. On the x-axis, you place the values of the variable, and on the y-axis, you indicate the percentage of cases. And for each category on the x-axis, you use a vertical bar to indicate the percentage of cases in the variable that take on that value. Here is an example of a bar graph for the candidate selection variable. On the x-axis are the variables 1 to 9. On the y-axis is the percentages, and each of these bars represent the percentage of cases in the variable that take on the values in each of the categories. So for category 2, about 27% of cases in the variable take on a value of 2. Clearly, 2 is the mode in this variable, as it is the value in the data set that is the most common. For interval and ratio level data, you can use a histogram. On the x-axis, the values represent ranges in your data. So for example, you could have one category devoted to values between 0 and 10, another devoted to values between 10 and 20, and you can keep going. And on the y-axis, you indicate the percentage of cases, and for each category on the x-axis, you use a vertical bar to indicate the percentage of cases in the variable that take on that value. Here is an example of a histogram for a variable that measures the strength of upper chambers of legislatures for different countries. 0 means a legislature is unicameral, and as the values approach 1, the upper chamber becomes as powerful as its respective lower chamber. Since this is a ratio level variable, I used a histogram to display its dispersion. As you can see, the first bar represents values between 0 and 0.16. The second bar represents values between 0.32 and 0.5. The third bar represents values between 0.5 and 0.68. The fourth bar represents cases between 0.68 and 0.84. And the last bar represents cases between 0.84 and 1. The largest category is 0.68 to 0.84. About 28% of cases are in this category. Once again, making bar graphs and histograms by hand is cumbersome. It is a lot easier in Stata. To create a bar graph or histogram in Stata, click on the Graphics button, then select Histogram. In the variable box, select the appropriate value. Indicate whether the value is discrete or continuous. It is discrete if it's an ordinal level variable, otherwise it is continuous. In the y-axis box, you should always click %. And you can edit the axes titles here and here in the y-axis and x-axis tabs. Then you would click OK. So, as an example, I will do the candidate selection variable. It is discrete because it's ordinal level, %, and I will click OK. And the graph should pop up here. Just as a side note, the code for your graph will be here if you want to save it in a do file to replicate it later. In addition, remember that you can copy and paste your graph into a Word document. So after you make your bar graph or histogram, you have to interpret it. If your graph looks similar to this graph, your data are normally distributed. That means the mode, median, and mean are very close together. If your graph looks like this, it means your data have a negative skew. A variable has a negative skew when the mean is less than the median. This means that there are a handful observations in this variable that take on extreme low values, and they are dragging the mean in a negative direction away from the median. As you can see here in this graph, most observations are clustered here, but there are a few down here that are pulling the mean in a negative direction. As a result, the mean of 12.5 is less than the median of 20. Alternatively, if your graph looks like this, it means your data have a positive skew. A variable has a positive skew when the mean is greater than the median. This means that there are a handful of observations in this variable that take on extreme high values, and they are dragging the mean in a positive direction away from the median. As you can see in this graph, most observations are clustered here, but there are a few up here that are pulling the mean in a positive direction. As a result, the mean of 46.9 is greater than the median of 40. And finally, a variable can have a bimodal distribution as well. This happens when the variable has two modes. Here is an example of a variable with a bimodal distribution. As you can see, there are two modes, around 50 and 150. About 9% of the observations take on values of 50 and 9% take on values of 150. 50 and 150 are the most commonly repeated values in this dataset. There are two modes. While bar graphs and histograms are nice ways to visually display the dispersion of a variable, a more sophisticated way to measure dispersion is the variance, S squared, and the standard deviation, S of a variable. The variance and standard deviation of a variable give you a specific numerical value to identify how dispersed observations in your dataset are. The variance is calculated by subtracting the mean of the variable x bar from each individual observation xi. This tells us by how much an individual observation's values deviate from the mean of the variable. If an individual observation takes on a value close to the mean, this calculation should produce a value that is close to 0, meaning a small deviation from the mean. If an individual observation takes on a value far from the mean, this calculation should produce a value that is far from 0, meaning a large deviation from the mean. Now we want to know on average how far away these individual observation values are from the mean. We could take the arithmetic average here by adding all these values together and dividing by the number of observations. However, if we did that, the negative values would cancel out the positive values and we would lose information. Instead, we square the values to get rid of the negative numbers. Then we take those values, add them together, and divide by the number of observations minus 1. This calculation is very close to the arithmetic average. What the variance tells us is the average squared deviation from the mean. A squared deviation, however, is not useful information because when we squared the deviations from the mean here, it made them larger, making it look like the observations deviated much more greatly from the mean than they actually did. To bring the variance back down to a more realistic value, we simply take the square root of the variance. This calculation is called the standard deviation. It approximately tells us on average how often does each observation deviate from the mean. Now I will go through the steps on how to calculate the variance and standard deviation of a variable. I will use the party control over candidate selection variable as an example. First, you calculate the mean of the variable. The mean I calculated was 4.2. Then you subtract the mean of x from each individual observation. There were 987 observations in this data set. I'm only going to show you 2 in this example. However, I did do this for each observation. So for observation 1, the value of candidate selection was 2. So 2 minus 4.2 is negative 2.2. For observation 2, the value of candidate selection was 7. So 7 minus 4.2 is 2.8. I continued this process for the rest of the observations. The next step is squaring the values from step 2. Negative 2.2 squared is 4.8. 2.8 squared is 7.8. I continued this process for the rest of the observations. The next step is adding all the values from step 3 together. The sum of all the observations is 3,392.1. The next step is dividing the values from step 4 by the number of observations minus 1. 3,392.1 divided by 987 minus 1, or 3,392.1 divided by 986 is 3.4. So the variance is 3.4. The last step is to take the square root of the variable to get the sample standard deviation. The square root of 3.4 is 1.85. Now we can interpret the standard deviation to describe the dispersion of the candidate selection variable. We can say, on average, observations deviate from the mean of 4.2 by 1.85 units. Obviously, calculating the variance and standard deviation by hand is a great deal of work. Luckily, we can have Stata do it for us. In Stata, you simply type in some var name into the command box and click enter. As an example, I will have Stata calculate the standard deviation for the candidate selection variable. I type in sum can_select into the command box and click enter. After running this command, Stata will display the deviation for the standard deviation for the variable. For the candidate selection variable, it was 1.854738, which is really close to what we calculated in the previous slides. To find the variance for a variable, you simply can take the standard deviation and square it using a calculator. And this is the end of lecture 2.